please do go ahead and give us your presentation. Thank you, David.
Okay, terrific. Thanks, Rob. Yes, my name's David Rapson. I'm the CEO of FCT ACTech, and today I'd like to present some exciting results from a cement plant that shows the benefits of an at-line raw mix control system. So there's been some recent advances in technology that have made at-line control more effective and more affordable. And I'd like to show you how this type of equipment can actually simplify the control of a cement plant. So there are lots of variations that occur throughout the cement process, but there are things that we can do to reduce them. One of these ways is by choosing raw materials that have a consistent properties, or we can choose them from a single source. There are many techniques that can be used to reduce the variations as well, and these include mixing, blending, and homogenizing, many of the things that you'll all be well aware of. But every plant will be using these techniques to reduce the variations at each stage, but it doesn't always do enough for what we need. Sampling and testing at key locations in the process will reduce the variability and eliminate the out of specification materials that occur from time to time. But more frequent testing offers a greater insight into the process, and with well-chosen controls will reduce the operating costs and improve the operation of the plant. So variations cost sustainability, and what we mean by that is that we need to make allowances, and operating targets are based on quality requirements. Often there's a hard limit with those, and there's an offset that is required because of that variation that occurs. We can get closer to the target if the variability is less, and that's really what we're trying to do all the time. So one good example of this is limestone addition to cement. So when limestone is added to cement, it replaces the clinker. And for every 1% of limestone that we add, that's 1% more production that we can get effectively, or 1% less CO2 emission. So in a modest sized cement plant, it's possible to save about 20 tonnes of CO2 per day. And that's based on the carbon dioxide coming out of the limestone, the fuel and the electricity to run the plant. So it may not sound like very much, but that adds up over a year, and depending upon which country you might be in, there can be a cost associated with that emission. So it doesn't take long to provide a significant result from what seems to be just a small improvement in the process. So reducing variability of all the inputs to the kiln will improve its stability. So we've got things like the raw materials, the fuels, even the alternative fuels, recirculation and kiln dust. Most of these streams are tested, and often every 2 to 4 hours, but a lot can happen between those tests. And that's where expert control systems can help, but with more data they can do even better. And certainly with more frequent information they can make better adjustments. So at-line and online control has been wanted for decades. And one of those examples has been the cross-belt analyser, which was one of the first types of this equipment. Sampling is more frequent, and it's often automated, which means it's going to be more consistent. Software has also developed a lot in recent years, and it is now able to do complex calculations very quickly. So recent advances in computing power, X-ray detectors, low-power tubes have all improved enormously, making online equipment much more affordable than it ever has been. There are several locations in the cement process where materials are regularly tested. And a lot of effort is spent analysing and managing the raw materials because they will influence the operation all the way through the entire system. It is customary to check the raw materials prior to the raw mill, but some plant configurations have kiln dust recycles, which are not always accounted for and therefore cause variability to the kiln feed. Managing the heat input to the kiln is also critical to quality and minimising operating costs. While alternative fuels can reduce operating costs, they can also increase variability, and that means they need careful management. In the cement milling stage, there is also materials that get brought together that can vary, so it's good to control these as well to ensure we have a consistent product. There are new generations of at-line analyzers available now that are very accurate and can give results every 1 to 2 minutes, depending on what type of analysis is required. They can use XRF techniques to measure elements, or they can use XRD techniques to measure minerals. So one major advantage of these new machines is that they do not use radioisotopes, which can be very costly and require lots of paperwork. These units are rugged and are designed to operate in the field, close to the sampling point and often directly underneath the sampling point. In many applications, little or no sample preparation is required because it all gets done inside the unit. The analysis results are not affected by layers of material, which can often be a problem with other techniques. The data results from these analyzers are often sent to the plant process PLC and then can be used by any proportioning software that might be available. These units are designed for process control and provide many times the data, which gives us new insights about the operation of the process. So what I have here is a case study about where an at-ine analyzer, raw meal analyzer, has been installed into a very progressive cement plant in the USA. This particular plant is producing around 1.7 million tonnes per year, and they want more consistent feed chemistry to improve their kiln operation, mostly because they've got a pre-blend heap system, which creates off-spec material each time that they change from one heap to the next. To try and overcome some of the problems with these pre-blend heap systems, they have installed a cross-belt analyzer on the limestone, and they've also installed a second cross-belt analyzer to monitor the material from the Chevron stacker reclaimer system, but they've still been having problems with that. In addition to all of this, they've got some other difficulties managing the feed materials. One of them is the coarse material that comes from the raw mill. So that's the largest stone that sometimes gets knocked out the side, and that gets sent back into the limestone feed bin, which alters its composition. They also have a kiln dust recycle that is added into the raw mill after the raw mill, which means that's not accounted for either. And so what they do is they use estimates for these things, but it's not always possible to get the composition exactly right for all of these streams that are going into the process. So this is the, on the right is the plant raw meal air slide, and underneath the air slide is a simple RAM sampler. And this is the same sampler that they've been using for years, and this sampler will continue to be used for the online control analyzer. So what happens is the material falls from the air slide and it goes down into a small hut, which is located underneath the air slide, and that's where the analyzer is housed. So the plant PLC controls the entire system. And basically, when the analyzer requests some sample, the PLC activates the sampler. And the idea is that the analyzer maintains a constant rate of material going through the analyzer. So it uses about 1 cup of material per minute through the analyzer. So it has level sensors, which are used to start and stop the sampler so that there is a continuous flow of material through the analyzer. So this is the XRF raw meal analyzer mounted on its automatic sample return system. So this is the return system at the bottom here, obviously the analyzer at the top. So the raw meal drops down from above into the analyzer. where it is mixed and prepared continuously for the sample presentation system. So as I said, about half a cup of material passes through the unit each minute, and after it's gone through the analyzer, it drops out and then it's pneumatically conveyed back into the process. So also down the bottom here, we've got a bucket, and that's used to take a composite sample, which is used for the laboratory. So the analyzer provides elemental data to the process computer, which then compares its set points for the silicon, calcium, alumina, and iron. Based on those results, the adjustments to the feeders are made and the appropriate changes will happen. By checking a composite material that's passed through the analyzer, any drift can be compensated for. So this composite sample effectively becomes an outer control supervisory loop for the system. So this is a screenshot from the control room showing the feed silos and their whey feeders. And because of the operation of the whey feeders, they're able to produce a very accurate proportioning control system. There's one difficulty with this system, and for this particular plant, the material coming back from the pre-blend stockpile ends up into this bin here on the right. And the difficulty is that there's also the rejects from the raw mill table coming into here as well. So that means that they've not been analysed in any way prior to getting into this bin. So the proportioning system doesn't know about that material and it's going in. And so there's, depending on the amount of that material, it can cause difficulty with getting the chemistry on target. So what I've got here is a graph of the laboratory analysis results taken every 3 hours over a 3-day period. And you can see the results here for the silica, the calcium, iron and alumina. And what's indicated here with the green circle is a very high silica reading. And that's indicative of a pre-blend heat change. So what we know is that at this time, there's been a pre-blend heat change. And other than that, that's about as much information that we can see from this graph. But what I've done here is I've added the 1 to 2 minute data from the online XRF machine and superimposed it with the lab results. And what you can see here is that there's a lot more information that can be gathered. So we're presenting here 3 days worth of information sampled, as I said, every couple of minutes. And so it's very obvious where the pre-blend heat changes occurred. The silicon has shot up and then it's come back down again as the reclaimer has moved into that heap. So just adding a bit more information onto this graph, and I've got a line here, and this line is representing the point at which the automatic control system was turned on for the very first time. So you can remember back here, some sort of 6 hours prior, we had the heat change, and there's a reasonable amount of variability in that heap. And then at this point, we've turned on the automatic control system and it started to manage for the very first time the operation of the feeders. So despite not being fully tuned, you can see that the silica and calcium trends have stabilized very quickly once that software has taken control. It's also obvious down here that there's a few things that need to be tuned, and that was all part of the commissioning process. So I've got some results here of the Clinker. So the graph on the left shows about a month's worth of results of Clinker before the automatic control system was put in place, and then another month worth of data afterwards. So the plant has been able to make use of this reduced variability because the kiln has been much more stable. And as a consequence of that, they've been able to increase their C3S target from 60% up to about 64%. And they wanted to do that so they could get some additional cement strength gain So this is something that they weren't able to do previously because of stability reasons with the kiln. So here I've presented that same Clinker C3S information in a slightly different way, and I've used a box and whisker plot, which is a statistical way of presenting the information. So what it shows here is all of the data is listed between these lines. 50% of it is in the box and 50% of it is outside of the box. What's also here is a line, and that line represents the median value, and then X is the mean. So what this is showing is basically where the majority of the data is lying. So for this example, at this plant, before the online analyzer was implemented, we can see that the range of results is represented by the height of the orange box here, and we can see that that is reduced down. So what they've been able to do is reduce the variability at the same time as getting this additional increase in C3S, and we've also got the standard deviation results to confirm that over here as well. So the plant's been able to run at higher C3S with a reduced standard deviation at the same time, and that's something they just weren't able to do prior to the introduction of the raw meal analyzer. So this time I've got the Clinker results, but here we're looking at the freelime, and again we've got freelime data for 1 month before the introduction of the online analyzer, and the freelime data for another month after the analyzer. So there's quite a broad spread in this data, and particularly the one on the left, which was the beforehand, and it's these high points that are of interest because they represent very unstable kiln operation. And what we can see is that even with increased C3S, which previously did cause stability problems, we're not seeing that same spread of high values. So it's showing that the analyzer has helped stabilize the kiln. So the average freelime is now a little bit lower, but it's still within an acceptable range, and being able to run at this higher C3S level. So the plant has been able to use this increased kiln stability to increase their strength, their C3S target, which will in turn give them more strength, while only reducing the freelime slightly. So again, box and whisker plot again showing the data. We can see here that the outliers are much more visible in this type of plot. So very, very clear with this type of display that it's these high values that have been causing the stability issues. So we talked to the plant operators and tried to get some idea what they thought about all of this, and they were very much happier, basically because they found the mix was easier to burn and the kiln was much easier to control. So one of the important factors for them was the fact that they were able to adjust their C3S target up from 60 to 64, because before they had to target that lower C3S value simply to get better kiln operation, and now they're able to target 63 to 64 and achieve much higher early strengths. So another comment here was that now that the analyzer reports as soon as the composition goes off, and the software starts the correction process right away. So basically what they're able to do is let the system run, and if there are any problems, it will tell them about it. So in summary, this case study has shown that using an at-ine analysis of raw meal for mix control will stabilize the kiln, and the clinker will be much easier to burn. The more stable kiln, the plant was able to choose to increase its C3S target so that it could increase strengths, something that they were never able to do before. So the increased sampling frequency of the raw meal has revealed variations that could not be seen with the laboratory testing. So the addition of at-line data included the kiln dust and the raw mill recycle material, which gave more accurate control of the feeders, further reducing the variation. So the at-line analyzer has shown that it is an essential tool for stable kiln operation, and it's enhanced clinker quality significantly at this plant.
Right, David, you appear to have finished. So thanks very much indeed for your very interesting presentation, and for giving us some pretty interesting some pretty interesting statistics there about how your machine has improved production at those plants. Thanks very much indeed. Well, I'm very pleased to say that our audience has been paying attention and has asked plenty of questions already. I'd like to remind the audience that they can continue to ask questions just using the questions tab. But let's make a start on these questions, David. So the first one is from Bladar Kola, and Bladar asks, does the system consider any possible blockage of raw feeding which may affect the measured chemistry?
Well, yes, I mean, it depends on how the software is set up. It can be used to trigger alarms for various types of feeders as well. So I guess that's what you're talking about. So that functionality comes part of the software rather than with this type of analyzer. So there are a number of people that provide that software, and I'm sure that they include that in there with that functionality.
Right, and Bledar's got another question, a follow-on question, if you like. He says, isn't the measured standard deviation of your C3S at 3.6 rather high? He suggests that even without an automatic system, usually the C3S standard deviation is no more than 2%.
This is taken from a real plant, and this is the way they're operating. So the variability is going to be dependent on what equipment they've got installed. Obviously, stacker reclaimer systems are quite old technology now. They've probably been around for probably nearly 50 years, I would think. And so they're not going to be as efficient as some of the newer systems that would be using proportioning bins and higher grade, more consistent material. So I think, yes, if you've got a larger plant with different equipment, it is possible to get much better results. These guys know that this is not as good as, I guess, what you call world best practice, but they've certainly been able to make some improvements on where they were.
Right, okay, so what you're really saying is that the high standard deviation of the C3S is not down to your instrument, it's actually down to the rest of the plant providing higher standard deviations.
Yes. Yes.
And your machine is actually accurately measuring that situation.
It is, and it's been able to reduce the standard deviation down from where they had it. That's right.
Yeah, which in fact is a major accomplishment in itself, and actually reason enough to get one of these at-line analyzers.
Yes, correct.
Yeah. So Alexander Schleminger says, David, can you please specify if there is any sample preparation or pre-treatment necessary before analysis?
Well, for this particular machine and for raw meal, which it's measuring, no, there's nothing that needs to be done. It comes straight out of the air slide. It drops straight into the analyzer, and the analyzer takes care of the preparation that is required before it gets presented to the X-ray beam. So the machine has a built-in equipment to do that sample preparation. Yes.
Okay, so what's the particle size from the raw meal that you're analyzing here?
Well, the raw meal size is not that critical. Certainly, material that can be more than 20% on 90 microns is quite acceptable, but material coarser than that can also be accepted as well. So it's not particularly fussy. It's not pulverizing material like what might be a custom inside a laboratory or something like that. So it is doing no grinding or any other processing of the raw meal that's going into it. It just accepts it for what it is, examines it with the X-ray, and then presents the results.
Right. Okay. So it's not milling it in any way. It's not doing anything to it.
No. So the same would apply for cement. If cement was to be presented to this machine, no sample preparation is required at all. It just goes straight in. That's right.
Okay, and so I guess some people may be saying or thinking to themselves, okay, if you were to mill the samples, for example, would you actually see any difference in the compositional analysis numbers that actually come out?
Our results show that there's been very little difference. What we're doing is quite a different approach. So what we're doing is we're actually measuring all of the sample that's going through the machine all of the time. So if you were considering a lab analyzer, you might be measuring 10 grams of material. We're not. We're measuring 150 grams of material a minute. And if we were to average that over 2 minutes, we're probably looking at 300 grams of material. So statistically, we've got way more material to look at. And because of that, we can get the accuracy that's required. So the accuracy is, while it's not as good as a laboratory machine, it's very comparable, and it is quite capable of providing additional information, which will give far better process control.
Right, okay. So there's another question that's come in from Abdu Suzo from the University of Stuttgart. And Abdu says, can this concept be used for fuel additive mixing to control combustion outputs in a fuel combustion process? And has it been implemented anywhere right now? So can it be used to analyze fuel inputs?
I mean, we've got two different variations of this machine, and one of them uses XRF techniques, another one uses XRD techniques. So XRD techniques is looking at minerals. XRF techniques is looking at elements. Now, I'm not sure what type of fuels they might be looking at. Certainly coal is going to be something that would be considered, and on the basis of it being ground fine and presented through the machine, yes, it can do it. Whether it's able to pick up all of the things of interest in there is going to be another matter. So, I mean, I think coal's normally measured with a different technique because it's able to better pick up the properties that are looked for. But look, certainly I'd be happy to talk to those people and see whether we can actually do something for them. But yes, that would be an interesting application to work through.
Absolutely. Okay. Well, I'll get you guys together after the session today. So Gavisa Demisi says most of the time we suffer from more heat on the preheater and less heat in the kiln. He says, what could be the chemistry or reason for this? I'm not sure that you can answer that. I think that might be a question for somebody else, but do you have any insight on that at all?
Yeah, look, I'm a process engineer from way back, and yeah, look, there's a lot of things that can be causing that. Obviously, efficiency of cyclones, production feed rate, types of fuels that are being used. In fact, even just the mechanical condition of the cyclones is often attributed to those sorts of things happening. So yeah, look, many things there, and it's a matter of talking to some process specialists, I think, to work that one through.
Yeah, sure. Okay, so another question is coming from Abiola Saka, who says, thank you, David, for such clear delivery. So thank you very much indeed for that. The question from Abiola, though, is can we consider the coefficient of variation over standard deviation in quality assurance statistical analysis?
I've not actually looked into that exact parameter to see what's going on. I've sort of stuck to sort of the basic standard deviations and then looked at some of the, I guess, probability related parameters. So really what we're trying to do is make a bulk change in what's going on, and certainly the information that we've got here, both statistically and process-wise, is confirming that. But again, look, I'm happy to talk about that afterwards if you like.
Okay, and I think a final question is from Daniela Tomek-Hazivar, who says, in the case of raw mix control, do you also provide the control software?
No, we don't, but there are a number of suppliers that do this. Some of the larger equipment suppliers, the European suppliers, provide that type of equipment, a software that goes with their equipment. But there's also a number of independent software houses. We know some based in North America, and there's also some based in Europe that are able to provide that software. And it connects directly to the plant PLC system. It gets the data from the analyzer, and then it feeds the set points back to the feeders in the plant. So there's a couple of ways of doing it. Yeah, but there are options there, which include the OEM suppliers as well as some independent third-party providers of the software.
Very good. Okay, David, that's all the time we've got for questions at the moment. But once again, I'd like to thank you very much indeed for your very interesting presentation and for answering all our very many questions. Thank you very much indeed.
Not a problem. Thanks, Rob.
Thanks a lot, David. We'll see you again another time soon, hopefully in the real world.
Yes.
Thanks a lot, David. Bye for now.
Thank you.